Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics, lecture number 28. Before starting this lecture, let me review what we have studied so far in the current topic, series solution of the differential equations. In last two lectures, we studied series solution of differential equations, power series method, ordinary singular points, series solution near ordinary points, and series solution near singular points. So, especially in the last lecture, we studied the series solution near singular points, types of singular points, and method of Frobenius. We started method of Frobenius, but we haven't finished it yet. So today we will be starting with this method of Frobenius, and we will finish this topic. I also solved 2-3 examples of series solution near ordinary point in the last lecture as well. So in last couple of lectures, we have studied this whole thing, series solution about ordinary and singular points. So today's lecture's outline is method of Frobenius, and then we will go on to solve the Bessel's equation of order 0. Bessel's equation is a very important equation where series solutions have been adopted to solve, and especially the method of Frobenius. So let's start with the method of Frobenius first, and then we will go on to Bessel's equation. Method of Frobenius, suppose that x is equal to 0 is a regular singular point of the equation. Let rho is greater than 0 denote the minimum of the radius of convergence of the power series. These two series, let's say if px and qx can be written as the series, px and qx have power series representation. Let's say px and qx both can be, because if x is equal to 0 is a regular singular point, then capital P and qx will be analytic functions. And if a function is analytic, it must have a power series representation. Alright? So that's why we can write px and qx in the form of series. Alright? If R1 and R2 be the two roots of the initial equation, we know that the initial equation is R times R minus 1 plus P naught R plus Q naught is equal to 0, where P naught and Q naught are the first terms here. P naught and Q naught, basically they come from the limiting value as x go to 0. Alright, so R1 and R2 are the roots of this initial equation, and we assume that one root is bigger than the second one, R1 is greater than or equal to R2. Then this solution, which is x to the power R1 multiplied with the series, gives you one solution corresponding to the larger root R1. So we call R1 the largest root, and the corresponding solution will be y1. For the second solution, it depends. Can we write this as the second solution or not? The second solution may be x to the power R2 and another series. But this is not always the case. Alright? This is the case only if R1 minus R2 is neither 0 nor a positive integer. If R1 minus R2 is not a positive integer, then we can say that this is the second solution. Alright? Then there exists a second linearly independent solution for x positive of the form x to the power R2. So it depends whether R1 minus R2 is an integer or not. If this comes out to be an integer, then this will not be the second solution. Always remember. So one solution comes from the larger root R1, and the second solution will come from R2 if and only if R1 minus R2 is not an integer. Alright? Corresponding to the smaller root R2. So this is the method of Frobenius. And again, the radius of convergence in both these series is described by the last two equations is at least rho. This is the same rho which we wrote here. If rho is the radius of convergence of these two series, minimum of that, let's say if this has radius of convergence 1 and this has 2, then rho will be 1, the minimum of these two radius of convergence. Alright? So that will be the case for the original, your solution as well. The same rho will serve as the radius of convergence for your solutions as well. Alright? Remark, if the roots R1 and R2 are equal, then there can exist only one Frobenius solution, it turns out that if R1 minus R2 is a positive integer, there may or may not exist a second Frobenius solution of the form described by this equation. So as we said, this will be the second solution if R1 minus R2 is not an integer. So if this comes out to be an integer, then this will not serve as the second solution. Then we will have to do something else. All right? So first, let's consider an example of Frobenius series solution. Find the Frobenius series solution of this equation. So we will follow these steps. So let me stepwise summarize this method. First of all, you will find P naught and Q naught. After finding P naught, Q naught, you will plug those values here. That will give you the initial equation. And then you will find the roots R1 and R2. All right? R1 will give you the first solution. Then we will check whether R1 minus R2 is integer or not. If it is not an integer, then this will be my second solution, and I will find the second solution as well. After this one, it is very similar to the ordinary point solution. Right? Once you have assumed this to be the solution of the given equation, then you will just plug this equation back in and compare the coefficients, find C1, C2, C3, and that will be your answer. All right? So that will be the scheme we will be following for this equation, because x is equal to 0 is a singular point here. The given differential equation can be written as, if I divide by 2x square, I will get 3 by 2x, and x square plus 1 by 2x square. Clearly, x is equal to 0 is a singular point. All right? Here px is this, qx is this. But if I multiply px by x, it will give me 3 by 2, which is analytic. Constant function is always analytic. If I multiply by x square, again, in the denominator, I will be left with 2 only. It's again analytic. So both xpx and x square qx are analytic function, hence x is equal to 0 is a regular singular point. If it is a regular singular point, it means I can apply method of Frobenius. So for method of Frobenius, I need P naught. P naught is limit x goes to 0, x px, which is 3 by 2. Q naught is x square qx, which is minus 1 by 2. All right. Hence, our initial equation is r times r minus 1. P naught is 3 by 2. Q naught is minus 1 by 2 is equal to 0. So r1 is 1/2, r2 is negative 1. The bigger root, which one is the bigger one? Bigger is 1 by 2. So I will call r1 to be 1 by 2, which is the biggest root. Since they do not differ by an integer, you see, if you subtract these two, r1 minus r2, it will give you 3 by 2, which is not an integer. It means I will get two linearly independent solutions, one for the bigger root and one for the smaller root. Both will give me the solutions, one with an and one with bn. So I will get two solutions exactly here, two linearly independent solutions, because the difference between the initial roots is not an integer. So one by one, I will calculate an and bn. Rather than separately substituting y and y2 in the given differential equation, it is more efficient to begin by substituting x or cn xn. Instead of doing them separately, right, instead of writing 1 by 2 and minus 1 separately, we can just write x or cn xn. Just once, it will save us some time. All right. If you replace this one, we will then get recurrence relation that depends on r, because r will stay there, so your recurrence relation will depend on r. If I replace this in my original equation, which was this, if I replace in this equation, I will arrive at here. Now the common range of summation is greater than or equal to 2. We must treat n is equal to 0 and n is equal to 1 separately. All right. Following our standard practice, the terms corresponding to n is equal to 0 will always give the initial equation. Remember that whenever n is equal to 0 will give you the initial equation. So you see from here, is it not the initial equation with c naught with n is equal to 0? N is equal to 0 term gives you the initial equation. This is exactly the same initial equation. The terms corresponding to n is equal to 1 yield this one, so it means c1 has to be equal to 0, because this expression is not 0. If r is 3 by 2, 1 by 2 or minus 1, this is not 0, so c1 has to be equal to 0. The coefficients of xn plus r gives us the recurrence relation, which is given by this, and this depends on r. So till here, your method was the same for both values of r. So I saved some time and got the relation. Now I will work for separate r's. Now I will take r is equal to 1 by 2 and get the values an, and when I will take r2 is equal to -1, I will get bn. Instead of writing cn, I will write bn, an and bn for different r's. So C1 is 0 for both the cases. Now we discuss the Frobenius series solution separately for both the values of r, 1 by 1. So when r1 is 1 by 2, you can replace the cn by an because we have to make it different. Alright, so an is an minus 2 and r is 1 by 2, so 2 times n plus 1 by 2 square, n plus 1 by 2 minus 1. So you get this thing. If you simplify, you will get this thing. With this formula, we can determine the coefficients in the first Frobenius solution y1. Alright, so in view of this C1 equal to 0, if I take n is equal to 2, it will come out to be a naught. A2 is equal to a naught divided by some constant, 14. A3 will be A1 by this, but A1 is 0, right? A1 is 0. If A1 is 0, then A3 is 0. Similarly, A5 is 0, A7 is 0. So all odd coefficients will become 0. Whenever n is odd, an is 0. So with n is equal to 2, 4, 6, 8, I will get the even coefficients, alright, which are coming out to be this one, A2, A4, A6, and so on. Alright. This is now yx is equal to, now what will be your solution then? Yx will be, because every coefficient has a naught in common, so I brought a naught out. X to the power 1 by 2 is written because r is 1 by 2, x to the power 1 by 2, and a n xn. And all the odd coefficients are missing because they are 0. Even coefficients will give you this solution. So you got one solution, which is y1 of x, a naught, x to the power 1/2, and this thing. For the second solution, when r2 is equal to -1, this is not of course r1, it is r2. For r2, I will write this recurrence relation with r is equal to -1, and I will call this bn. bn is equal to this and b1 is equal to 0. Again, b3, b5, b7, they will all be equal to 0 because b1 gives you b3 and b3 is 0 gives you b5, b5 0 gives you b7. So all odd coefficients are still 0, but with n is equal to 2, 4, 6, so on, we will get b2, b4, b6, and so on. So I got this solution as the second solution, y2 of x. So I got two linearly independent solutions. One is given by this, second is given by this. And if you want to write the general solution, you can easily do that. You can write the general solution by writing C1 y1 of x plus C2 y2 of x. Or it's already written here, A naught y1 of x plus A2 y2 of V naught y2 of x. Alright, so their sum will be basically the general solution. It already contained arbitrary constants A naught and B naught. So if you just sum this and this, it will give you the general solution of the equation. So this is basically the method of Frobenius, a little different than the usual power series method, because in the usual power series method we don't multiply by xr, and here we multiply by xr and determine the values of r before putting the solution in the differential equation. So let's do another example, which is basically the Bessel's equation of order 0. Find the Frobenius solution of Bessel's equation of order 0. Order 0 is not the equation of the order. Order of the equation is still 2. It's a second order differential equation. Here x square minus n square is the general Bessel equation. In y, it is x square minus n square. That n is 0 here. So we call the Bessel equation of order 0. Alright? The order of the differential equation is still 2. Now if I divide by x square, I will get y double prime plus 1 over x y prime plus 1 y is equal to 0. Clearly x is equal to 0 is a singular point, and it's a regular singular point, because if you multiply by x, you will get 1. It's analytic function. If you multiply by x square, you get x square. It's also analytic function. Both are analytic, so x is equal to 0 is a regular singular point. All right. So in this problem, x equal to 0 is a regular singular point, so we can apply the method of Frobenius. P naught is x px limit goes limit x goes to 0, which is 1. X square qx, which is x square, limit as x goes to 0 makes it 0. So P naught is 1, Q naught is 0. So initial equation will become P naught is 1, Q naught is 0. Initial equation becomes r square minus r plus r is equal to 0. So r square is equal to 0. Thus we obtain only one exponent r is equal to 0. And there is only one Frobenius series solution, because I got only one solution. R1 and R2 are the same. If they are same, then there is just one solution. So I can get x to the power 0 and goes from 0 to infinity Cn xn. This is basically a simple power series. It turns out that we are getting the simple power series. If we substitute this in the given equation and compare the coefficients, you will get C1 equal to 0 and Cn is equal to this. After finding the coefficients, Cn is 0 for odd n, and for even n you are getting these coefficients. So your solution is this. Alright, if I choose C naught, because C naught is arbitrary. C naught is arbitrary. So if I choose C naught to be equal to 1, it gives me this one, which is known as the Bessel's equation. This is J naught x. This series is called J naught x, which is the Bessel's equation of Bessel's function of order 0. All right, J naught x is known as the Bessel's function of order 0. Why? Because it comes from the Bessel's equation. Bessel's introduced this equation, and he found out the solutions of the equation, and he named the solution as Bessel's function. So this is the Bessel's function of order 0. All right. It is also noted that we are able to obtain only one Frobenius solution here. Only one Frobenius solution, which is J naught of x. If it's Bessel or not doesn't matter. If we have a differential equation where x is equal to 0 or any other point is a regular singular point, we can follow the steps of method of Frobenius to obtain the solution. All right. So following the same footsteps, I can solve this equation as well. So this is another example of the series solution. Find the Frobenius series solution of xy double prime plus 2y prime plus xy equal to 0. So let's do it. All right, so this is the example where x is equal to 0 is a singular point, regular singular point, and we need to apply the method of Frobenius to get the solution. So in standard form, this equation can be written as we have y double prime plus 2 by x y prime plus 1 y is equal to 0. All right. So clearly x is equal to 0 is a singular point. To prove it a regular singular point, we need to investigate it further. Here px is 2 by x, qx is 1. So x times px is 2, x squared times qx is x squared. Both are analytic at x is equal to 0. This implies that x is equal to 0 is a regular singular point. All right. So this is a regular singular point. So it means we can apply Frobenius, method of Frobenius. So before that, we will find the initial equation, and for initial equation we need P naught and Q naught. Limit x goes to 0, x px, which is 1. X px is 2, so this is 2. Q naught is limit x goes to 0, x square qx. X square qx was x square, so it is 0. So therefore, the initial equation is r times r minus 1 plus p naught r, which is 2r, plus q naught is equal to 0. All right. So this is r square minus r plus 2r is equal to 0. R square plus r is equal to 0. R times r plus 1 is equal to 0. So this implies r is equal to 0 and negative 1. All right. So we say R1 is equal to 0 and R2 is equal to -1. Now if you observe, R1 minus R2 here is 1. So it means it's an integer. So R1 and R2 differ by an integer, and we haven't studied this case yet, right? At the beginning we said if R1 and R2 they do not differ by an integer, then we can get the two linearly independent solutions. But if they differ by an integer, the second solution is not guaranteed. Let's see what happens. Alright, so because R1 and R2 they differ by an integer, so we cannot guarantee right now whether there will be a second solution or not. But in this case, when R1 minus R2 is an integer, it is better to begin with the smaller exponent, smaller root, right? Smaller root of R1 and R2. Basically R1, R2 are exponents, so we can call it. So in this case it is better to start with the smaller exponent. Our recurrence relation will then tell us whether there exists a second solution or not, second Frobenius series solution or not. Because right now we don't know whether our Frobenius series solution exists or not. Alright? So if it does, then of course we get both the Frobenius solutions, and this will be a lucky case, a fortunate case, that even we had R1 minus R2 as an integer and still we got the two Frobenius solutions. That will not be always the case. That's why I'm calling it fortunate case, that this is very fortunate here in this example, that even the difference was an integer and we got two linearly independent Frobenius series solutions. Alright, that will not be always the case. So if it does, if the second solution does exist, if it does exist, then our computations will simultaneously yield both series solutions, both Frobenius series solutions. Right now we can't say anything. Frobenius series. Alright, so let's start with the series solution and get the recurrence relation first. So we are starting from the smaller exponent. Alright, so let y be equal to x to the power -1, summation n goes from 0 to infinity, Cn xn. Alright, and which we can write n goes from 0 to infinity, Cn xn minus 1. And now take the two derivatives. Y prime will give you n goes from y double prime will be n goes from 0 to infinity, Cn n minus 1, n minus 2, xn minus 3. Here I am writing again from 0 to infinity because the first term will not drop out here. You see, the first term here is c naught x to the power -1, and the derivative will be c naught x to the power -2. So c naught is not dropping out. So if I start from 1 and goes from 1 to infinity, it means I'm not writing that first term, which is c naught x to the -2. Similarly, the second derivative will be c naught x minus 2x to the -3. Again, if I started from 2, then I will be missing the first two terms. But the second term, which is c1, is becoming 0, and that's not a problem. It will become 0 automatically. N is equal to 1 will give you 1 minus 1, 0. So there is no c1 term, which is of course dropped out after the derivative. So therefore, our original equation, let's call it equation 1. 1 will give, therefore 1 gives x times second derivative 0 to infinity Cn n minus 1 n minus 2 x n minus 3 plus 2y prime. So plus 2y prime 0 to infinity Cn n minus 1 x n minus 2 and plus xy. So x times y is 0 to infinity Cn xn minus 1 is equal to 0. So if I multiply x inside, this will become n minus 2 xn minus 2 and plus 2 times n minus 1 Cn n minus 2, and at the end it will become n plus 1 Cn xn is equal to 0, because multiplying x inside, it will become n minus 1 plus 1, it will become xn. So now I need to change the index from, this is xn, so I need to change this index to n and this index to n. So in the first term, if I replace n by n minus 2 by n, then this will become n will become n plus 2. So Cn plus 2, n plus 2 minus 1 is n plus 1, n plus 2 minus 1 is n, and xn. And now because n starts from new n is n minus 2 basically. So if n starts from 0, the previous one will start from negative 2. Because n is equal to 0 gives you x to the power minus 2. So here n is equal to 0 will give you 0. So we don't want this. So it should start from minus 2 to infinity. Similarly, here I am changing n minus 2 to n. So again, n will become n plus 2 minus 1 is n plus 1, Cn plus 2, and xn, and again n will start from minus 2 to infinity. Because n0 gives you x to the power minus 2, where n minus 2 will give you x to the power minus 2. Alright? And plus, here we don't need to do anything, so this will remain. So I shifted the index in the first two terms. Shifted index in first two terms. Alright? This will become this and this becomes this. Shift of index in both cases. Alright, so from here, xn is same, so we have no problems. But this starts from n is equal to 0. It means I should deal with n minus 2 and n minus 1. In both the cases, I should deal with them separately and then start from 0 to infinity. So n minus 2 term will give you C0, minus 2 plus 1 is minus 1, and n minus 2. So minus 2 times minus 1 is 2. So 2c naught x to the power minus 2. Alright? Plus negative 1. So negative 1 will make it 0. Minus 1 plus 1 will make it 0. So you are gone. So you got n is equal to 0 to infinity Cn plus 2 n times n plus 1 xn. And here, if you replace n is equal to minus 2, you will get minus 1 minus C0 x to the power minus 2. And if you replace n is equal to negative 1, this will be 0. And then you will start with 0 to infinity Cn plus 2 n plus 1 xn. Alright? And then the last term will remain as it is because it's already starting from n is equal to 0. So this is what you got. Now I can combine these three summation terms and I can write this x square separately. So minus 2c naught x to the minus 2 and minus 2c naught x to the minus 2, they cancelled out. So I'm left with summation n goes from 0 to infinity. Inside you are left with n plus 1 Cn plus 2, n plus 1 Cn plus 2, and here n plus 1 Cn plus 2, n plus 1 Cn plus 2 is 2 times, I guess, 2 times, because this 2 is being multiplied. So 2n plus 1 Cn plus 2n plus Cn plus Cn. xn is equal to 0. Now if you simplify it, this inside thing, n plus 1 cn plus 2 is common, so you got n plus 2. So it is n plus 2, n plus 1, cn plus 2, n plus cn. So this is true only if these coefficients are equal to 0. It means cn plus 2 is equal to minus cn over n plus 2, n plus 1 for all n goes from 0, 1, 2, and so on. Alright, so this is your recurrence relation. Alright, so to get the coefficients, I will start by n is equal to 0. And 0 gives me c2 is equal to minus c0 by 2 and 1. Alright, n is equal to 1 will give me c3 is equal to minus c1 over 3, 2. Right? N is equal to 2 will give me c4 is equal to minus c2 by 4, 3. And because c2 is given as minus c1 by 2, 1, so this is minus plus c naught over 4, 3, 2, 1. And n is equal to 3 will give me c5 is equal to minus c3 over 5, 4. And if you replace the c3 value, you will get c1 over 5, 4, 3, 2. Alright, so it means you are getting c2 is equal to minus c naught by 2 factorial, c4 is c naught by 4 factorial, right? And from here c6 will be minus c naught by 6 factorial, and so on. Similarly, c3 is minus c1 by 3 factorial, c3 is 3 factorial, c5 is c1 by 5 factorial, c5 is c1 by 5 factorial, and c7 will be minus c1 by 7 factorial, and so on. So it means you are getting two arbitrary constants here, where c0 and c1 are arbitrary. So you see, you got the two, you will get the two linearly independent solutions just because of two arbitrary constants. So again, this is the lucky case. We were fortunate enough to get two solutions out of just one root, r is equal to -1. Alright, so this is not always the case. When r1 and r2 differ by an integer, this will not be always the case, and we will deal with them separately. Alright, so here if you go on and for even case 2n, you are getting minus 1 to the power n divided by 2n factorial. See, the same factorial, 2 for 2, 4 for 4, 6 for 6, and plus minus are changing. So it means you are getting this kind of thing, and it is c0, and c2n plus 1. So c2n plus 1 will give me this thing is minus 1 to the power n again, and c0 divided by again the same factorial, so 2n plus 1 factorial, c1, not c0. Alright, so you got this for n equal to 1, 2, 3, so on. And 1 give you c2, c3, and 2 give you c4, 5, 6, 7, 8, 9. So you are getting in pairs. So this is the case. So therefore, what is your solution? Therefore, y is equal to x to the power minus 1 and goes from 0 to infinity, c n x n. This was our solution at the beginning. So x to the power minus 1, I need to divide it into even and odd separately. 2n x 2n plus c2n plus 1 x 2n plus 1. Now x to the power minus 1 series, you have to first write n is equal to 0 gives you c0 plus c1x. Right, c0 plus c1x plus n goes from 1 to infinity, and for 1 to infinity we have this c2n is minus 1 power n over 2n factorial c0 x 2n, and plus n goes from 1 to infinity C2n plus 1 is minus 1 power n C1 over 2n plus 1 factorial and x to the power 2n plus 1. So this is what you are getting. Now if you separate C0 and this C0 term and C1 term, if you write them separately, you get C0 by x. This 1 over x is outside, so I brought C1 out, and inside you are getting a 1 plus this one. For n is equal to 1, you are getting minus x square by 2 factorial plus x4 by 4 factorial minus x6 by 6 factorial plus x8 by 8 and plus minus so on. This is what you are getting, and plus with C1 and C1 you are getting C1 by x, and C1 gives you x first, and n is equal to 1 gives you minus x cubed by 3 factorial plus x5 by 5 factorial minus x7 by 7 and so on. And you see these are well known series, since cosine x is 1 minus x square by 2 factorial plus x4 by 4 factorial minus x6 by 6 and so on, and sine x is x minus x cubed by 3 factorial plus x5 by 5 factorial minus plus so on. So you can see that this first one is cosine x and the second one is sine x. So therefore your y of x is C0 by x times cosine x, C1 by x times sine x. So your solution is C0 cosine x by x plus C1 sine x by x. All right. So you got two linearly independent solutions from just one root r is equal to -1. So this was the exceptional case basically. It's not always the case that whenever R1 and R2 will differ by an integer and you will get two series solutions. It's not always the case. All right. So here we were lucky that we got y1x and y2x. Right. So y1 and y2 are two linearly independent solutions. All right. So I didn't need to consider r is equal to 0. I just considered r is equal to -1. At the beginning, we just considered this one, the smallest one. I considered this one with r is equal to -1, you see here. All right. This is the case with r is equal to -1. And we got the two linearly independent solutions. We got two linearly independent solutions. So here, if it turns out that we don't get the second solution, if we don't get the two linearly independent solutions, then we will go back to r is equal to 0 and try to find out the new solution. All right, that may or may not be possible, but we will have to see. All right, so when you have this type of situation, when your r1 minus r2 is not an integer, here, when r1 minus r2 is an integer, then what we do is we try our luck. All right, we start with the smaller exponent, and we try our luck. If we get the two linearly independent solutions from here, that's fine. But if we do not get the second solution from here, then we go back to our larger root, and that solution will be guaranteed. Larger root will definitely give you the solution. All right, so we get one solution, and again the second solution we still don't know how to get, but we will study it later on, that how to get the second solution when we are getting just one solution from our regular way. In previous example, in Bessel's equation, when r1 and r2 the difference was 0, both roots were the same, we again got just one solution and we don't know how to get the second solution. Similarly here, if our smaller exponent does not give you the second Frobenius series solution, then we will get only one solution corresponding to R1, which is the larger root, and then we have to see what we can do for the second solution. But right now we don't know it. So we will of course have to have extra knowledge, and we will study it later on, that how to get the second solution when R1 minus R2 comes out to be an integer. So we will study the general case for that. This was not the general case, this was a special case where even though our roots differ by an integer, and still we were able to find the two solutions of the equation. Alright, so let's review the method of Frobenius once again, because it's little complicated than the solutions about the ordinary point. In solution about the ordinary points, we have a regular power series solution, and it's very easy. There is no trick at all. We just assume the solution of the form Cn xn, we substitute in the equation, we substitute that in the equation and get the coefficients done. Once we got the coefficients, we have the series solution. But in the method of Frobenius, we have a singular point, we have a regular singular point, and then the usual series, power series solution will not give you the answer. So what we do is we multiply by xr. Our regular solution gets multiplied by xr, like this one. Alright, then the term corresponding to n is equal to 0 gives you the initial equation, but we have a method of finding the roots of initial equation directly. Right? We can directly write this initial equation and find the roots R1 and R2. Then R1 an xn will guarantee one solution, where R1 is the larger root. This will guarantee one solution. The second solution is not guaranteed. If I replace R by R2, it may not be the true, but if R1 and R2 differ by a non-integer number, like if R1 minus R2 is not an integer, then there is a guarantee that there is a second solution of this form. So we have no worries at all. Alright, so what we can do is we can separately replace this into the given equation and get the solutions. Alright, we will get R1, R2, and we get the solutions. We did this example where we have found out R1 and R2 and get the solutions. It was a very precise example. Then we did another example where our initial equation gave us just one root, R square is equal to 0. So again, one solution is guaranteed here. R1 minus R2 is equal to 0 because the roots are equal. If roots are equal, then R1 minus R2 is equal to 0, and we are guaranteed only one solution. Alright, so how to find a second solution, we don't know right now. Alright, so if it's just one solution, I will obtain just one solution, which is given by this. In our case, this is just one solution, and how to get the second solution, we don't know yet. Alright, similarly here, if R1 minus R2 is a positive integer, it comes out to be a positive integer, then again we are not guaranteed to Frobenius solutions. Then what we do is we start with the smaller root and hope for the two solutions. In our example, which we did at the end, we got the two solutions, so we were done in that example, that we picked up the smaller root and we got the two solutions, so that's fine. But this will not be always the case. If we do not get the solutions from that smaller root, then we go back to our larger root and get one solution, because larger root guarantees one solution, one Frobenius solution. Alright, so we will go to that and get at least one solution of the differential equation. How to get the second solution, we will discuss it later on. Alright, so that is the summary of the series solution. So let me summarize this again, why I am emphasizing it more on this, because it's little complicated than the ordinary one. So as a summary, you have to first prove, right, that x equal to a is a regular singular point. Is a regular singular point. Usually we take x is equal to 0, but it can be any number. X equal to a is a regular singular point. Then our second step is initial equation. Write the initial equation. Right? Initial equation is r times r minus 1 plus p naught r plus q naught is equal to 0, where p naught is limit as x goes to a, x minus a px, and q naught is limit x goes to a, x minus a square qx. These are the two constants p naught, q naught. If we replace them here and get the roots, then we see whether r, let's say r1 is the larger root, then y1, which is x to the power r1 cn xn, gives one Frobenius series solution. This is guaranteed. You will definitely get this series solution. And then we go on to see whether r1 minus r2, they are differ by an integer or not. If this is not equal to 0 and is not an integer, if this is not equal to 0, means both roots are not equal, and also their difference is not integer, then y2, the second solution, is x to the power r2 series and goes from 0 to infinity. Cn, or you can just change it Cn bar or Bn, whatever you want to write, xn gives the second Frobenius series solution, and they both will be linearly independent. Frobenius series solution. Alright, and y1 and y2 are two linearly independent solutions. And you are done, because you got two linearly independent solutions for a second order differential equation. You are done. Alright, but if r1 minus r2 is equal to 0, alright, then one solution is guaranteed. Don't know about the second solution. If r1 minus r2 is an integer, alright, then we start with the smaller exponent, alright, and hope that it gives two linearly independent solutions, as was the case in our example. We did an example where we got two linearly independent solutions. Alright, but if smaller exponent does not give second solution, then we go back to our larger exponent and obtain one guaranteed solution, because that is again guaranteed against the larger exponent, guaranteed solution. Alright, so again, if we get one guaranteed solution, then how we'll get the second one, that is another discussion. We will continue with that, how to get the second solution if we are getting just one solution out of it. Alright, so this is the summary, and again I emphasized on it 2-3 times. The reason is that it's little complicated. If you do the practice, you can master this technique, but if you just leave it by just looking at me solving the equations, it will look very easy, and you will see that, oh, it's a very simple topic and you don't need to practice at all. If you don't practice, you will forget it. If you practice 2-3 problems on your own, then you will get to know what is happening. And with the summation notations, with the shifting of index, changing of index, it needs practice. Alright, so do practice, do pick some problems from any differential equation book, alright, and start doing some problems. Alright, if you do some problems on your own, then you won't forget this topic, as well as you will master this technique as well to get the series solutions about regular singular points. All right, so today in this lecture we studied method of Frobenius. We solved Bessel equation of order 0. Why I wrote it separately? Because Bessel equation is an important equation and Bessel functions is a totally different topic. So Bessel function is a solution of a Bessel equation, and we can study the properties and whatever you want for the Bessel functions. All right, so we will continue with the same topic, series solutions, next time. So thank you very much for being with me throughout this lecture. I hope you understood it. I'll see you in next lecture. Till then, Allah Hafiz and Assalamu Alaikum.